Okay. So recently, as of recently, we have a new stream on the Lean Zulip for Fermat's last theorem, Kevin Buzzard's 5-year mission to prove Fermat's last theorem in Lean, which I can presumably find on GitHub somewhere. Last theorem, Lean, GitHub. Not that one. This one maybe. This is not a GitHub page. Where could it be? This one, yeah. And there's a blueprint here. Now, I don't actually know any number theory, which might pose some problems for me, but I thought I would nevertheless maybe try to contribute something. Because in particular, if you go over here, there are these definitions, these like Z hat and Q hat that Kevin has been posting about. And this definition isn't actually that complicated, right? We have some like, indexed sequence of elements of Z mod n, and there's some like property about them. But some of these look like they might not be too hard. Like, for example, just like proving something is injective, or proving that the other map is, or like the intersection is something else. So I thought I might like try to find one. So I did like a bit of work. I just sort of like tooled around. I think what was I working on? I didn't like really clear it with the people who are actually organizing things. But if I go down to where the Git says that I've edited things, this is the injective rat function. So I guess this is this function, right? That this is an injective function. And I'm not really familiar with the API of some of the types here, but I nevertheless was sort of like attempting this the other day. So I thought maybe I'll like go and try and finish that up. Just before I do that, I want to make sure that I'm not going to do something that someone else has been working on. Outstanding tasks v3. Hurwitz quaternions. Yes, okay. Here for v2. I mean, is this like done? This element. Done. Natural map is injective. The naturals into Z is injective. But do we have the equivalent thing for Q? Hat? Q hat? You would think I would be able to see something similar. See hat. The maps. Okay, so this is the one, right? The maps from Q and from Z hat into Q hat are both injective. This follows from torsion freeness. Okay, this is interesting. The fact that that he's actually saying that there's something I have to know in order to prove this is a bit concerning. Flying flatness for Z. It will be a more low-level way to argue. Yeah, someone should like grant the capability for this to be for the docs search to work. follows from torsion freeness. So someone claimed some of these. Yeah, I don't necessarily see that anyone has done this. Maybe if I go to the GitHub, I think I was here, and I just have to navigate backwards. Pull requests. Update the blueprint. Okay, maybe like one thing that I should do. Yeah, maybe the first thing I should do is make a branch slash injective rat. Create a new branch. And I'll just go back over here. And in this branch, I'll add progress. Commit. Okay, I don't necessarily want to publish this branch yet. What I do want to do is pull from FLT main. What happened? Oh, I need to like tell it to merge. Cool. Let's try that again. Pull from FLT main. Yep, seem to be totally totally satisfied, which means that no one else has been presumably working on this or merging things that would conflict. So maybe I should like go and try and figure out what the actual mathematical justification is for this thing I was doing. So like, what is the thing that I have here? Let me like produce the produce this. So there's this. The theorem is this. This I1 is injective. So the first thing you do is you introduce a bunch of variables, and so what you're trying to prove is that I1 of A equals I1 of B implies A equals B, right? And I'm pretty sure what these are, right? So A and B are rationals, and I1 is this map into from Q into Q hat, where Q hat is defined as Q tensor Z hat. And so I'm pretty sure the map is this is the natural inclusion from Q into Q tensor Z. Now, well, I should say Q tensor Z hat. Now, Q tensor Z hat, I conceptualized that, right? Okay, so my experience from linear algebra tells me that this is just like a tensor product of two types, and that Q mapping into that is just the trivial map that takes Q to Q comma 0. But that might not actually be the case here, because this is, I think it's like a slightly more tensor, it's like a tensor product of modules, or algebromorphism, from A into A, tensor, R module tensor product with B. So it's a little bit more tricky. So I can do this, and I can unfold I, and this include left, and I can simplify with include left apply. So we get to this stage. So what we have is A And here we have the T-mul, which is like this tensor product. This is something that gives you an element of the sort of tensor product space. Like, in fact, if I can go to definition, this is like a new feature that they talked about. So T-mul is something that takes an M and it gives you one of the, but let me actually take a look at this type itself. This is the tensor product type. How is it defined? Tensor product. The tensor product of two modules M and N over the same commutative semiring. Yes, is this not just the set of ordered pairs? How is this different from the set of ordered pairs? Obviously, it's not the set of ordered pairs because then it would just be / times. Okay, so let me look at this weird type definition here. It's the add con gen, the inductively defined smallest additive congruence relation containing a given binary relation. Yeah, I saw this before. I wasn't totally sure I understood. Let me go to the definition here. Two additive. So it's a two additive. Yeah, okay. Congen rel. Okay, so congen. What is congen? The inductively defined smallest multiplicative congruence relation given a binary relation. Okay, so this is the relation, right? So if I have some relation, I'm going to get another relation. It's like some sort of completion of this relation, I guess. So I have some relation, I'm going to get out another relation, which includes all of the relations that we had at first, right? All of the relations we had at first. It includes reflexive, so it's the reflexive symmetric transitive closure of that relation. And then furthermore, it's also closed under mul. And what does this mean? So if we have it for wx and we have it for yz, then we also have it for wy and start for w times y and x times z. Okay. So two things are the same if a comma b, what am I trying to say? I mean, okay, so this is further complicated by the thing that we are taking. Where have I gotten to? The thing that we are taking a closure over is this tensor product equiv relationship, which has a whole bunch of further inductive things, right? So of 0, what is this? The relation on ad-free monoid that generates the congruence. Yes, well, this is a little this is a bit annoying as a documentation string. It's like, yes, this is the thing that gives you this thing. It's like a sort of circular documentation string definition that generates a conclusion whose quotient is the tensor product. Okay, so so it gives you two elements of m times n. So 0 times 0 comma something is equivalent to 0. And something comma 0 is equivalent to 0. So the idea that this is like the tensor product of modules is furthermore a module. I'm going to assume that's the answer is yes. Okay, so 0 comma anything is equivalent to 0. If I add two things on one side, yeah, okay, this is relevant to what I was doing. If I add two things on one side, that's the same as, so a comma c plus b comma c is equivalent to a plus b comma c. And presumably the other way around. And if I add two things, that's the same. I can do it in either order. So I get like the point of all of these inductive things is just there's like a whole bunch of equivalences that are true of this whole system. And so what was I looking at here? I was like, I observe this, right? I observe that this equals this, and the first thing I thought is like, okay, if I can subtract both sides, basically I sort of intuited enough. I think I even did this, right? So I subtracted on both sides, and I intuited that this would be possible, right? So I was able to do this. And the thing I noticed at this point is that, okay, I have this rational number a minus b, which is some rational number, and it appears twice, and a and b don't appear in any other way, and so this is like, I've essentially reduced the problem to proving that this implies that this for any rational number c, right? Like I could even proceed to do this. I could say something like, um, let I forget exactly how to do this. Like, so the first thing I do is be like, let c equals a minus b. Or maybe it's set c equals a minus b. Yeah, and then all of the other things go away. And then I like clear a b, but it's gonna fail. How do I get rid of how do I get rid of when I have like a let statement like this? How do I get rid of this? It's like I don't care actually how c is defined. I want to prove this for any value of c. Let me like try and recall. Clear let. I feel like I should even like search for. I should search in my own view messages sent. Clear let. Let remove introduce let in a sub-expression. That's not quite what I want. Is this, I'm trying to think. Is this what I was doing in the when I was doing that thing in the PCP linear PCP project? I was wanting to no in the proof of Schwarzschild. I was wanting to remove a let. I think there was something they were telling me how to do that. I feel like if I say clear. I'm sure it's this one. How to classify through an equiv. Clear value. There it is. Okay. So if I clear value C, now C is just another rational number, and I can clear A and B, and I've reduced the problem, right? So I've like, here's, yes, now I've produced the thing that I want to do. The thing I observed, and this is something that I feel like there could be even like some sort of form of automation about this, but I have been too lazy to try and implement it. It's like, I should be able to detect that like A minus B is like the only expression in which A and B appear, and so therefore I should be able to sort of, you know, this is equivalent to this, like provably equivalent to this in a way that should be like detectable and automatable. But this is what has to be proven now. Anyway, so Yes. So what have we achieved, right? We have C is some rational number. One is in the Z hat, right? This special Z hat ring. I guess it's a ring, right? It's a special ring. I don't know, this Z hat thing, the profinite completion of Z. And so, yeah, seems like this should be easy. Seems almost like this should be like a basic simp-lemma. Yeah, it would seem that way, wouldn't it? That this would almost be like some sort of basic simp-lemma, but simp does not solve the issue here, I believe. If I run simp, it just doesn't work. If I run like asop failed, made no progress. Right. I mean, I think the other way is sort of obviously true, right? The issue, right? So the question is, how do I go ahead and prove this, right? I mean, one question is this something that's true for any pair of rings, right? So I have Q and some arbitrary other ring R, which is also a Z module, right? They're both Z modules, of course, because they're rings. But is it immediately the case that this is going to be true? So 1 is not equal to 0. So obviously, if 1 were equal to 0, it would have to be in like a non-trivial ring, probably. It would have to be a non-trivial ring. I wonder if it's not been proven that it's a non-trivial ring. What happens if I instance non-trivial Z hat? Okay, so it has been proven that that's true. But it's simp. But simp doesn't do it. Okay, so I was just wrong. It has in fact been proven, probably somewhere above in this very same file. Yeah, that it's non-trivial. Cool. Okay, but this breaks the theory that there's some lemma somewhere in the library, because I would assume that there would be some like lemma somewhere in the library which says that if R is some non-trivial ring, and if I have C tensor mole like something that's not equal to 0, 1, this is 1 of type Z hat. The thing that I would be interested in is something that like sounds like T mul peak 0. Let me open up the documentation. Docs for MATLAB. This one. Like T mul. Thing is, it doesn't even really give me T mul. Tensor product.T mul. Like, what lemmas do we have in existence about T mul? So T mul sub, I applied sub T mul, right? I applied that one at least. T mul 0 is just going to be something of the form which is the opposite, right? It's going to be at like if C tensor 0, like C tensor 0 is equal to 0, is just what it's going to be. Yeah, this is just some basic theorem that comes directly from that inductive unique. What is the unique type class? This is interesting. with a unique term default. Extends inhabited. Okay, interesting. Compatible SMAL, SMAL TMAL. I don't think this is necessarily useful, is it? Right, this just lets me like move things from one side to the other, which is not going to be helpful here. Right. So like what would this tell me? Yeah, not anything, I think. SMAL TMAL. And I seem to be getting away from TMAL definitions. I mean, the key question is, how do you know that two things are not equal? Because like this is sort of the tricky thing, right? Basically, the axioms tell you just a whole bunch of things are equal, and nothing is equal if it's not one of those things. So it's not necessarily the case that you can just prove easily that something is not equal to 0. Right, contrapositively, we could be using C is not equal to 0 to prove that this is not equal to 0, but it's hard to prove things are not equal in this ring because it's not how it's defined. I'm also not like entirely sure I understand like what the nature is of this ring, right? I think it's like, let me go back to the definition of it. Free ad monoid. Where's the definition? Sorry, go to the definition for this. TMAL. So this is ad con, the free ad monoid. Right, okay, so if I actually go here, the tensor product is defined as the quotient, right? The quotient by an additive congruence of a type with an addition. Right, so two things are equivalent if they can be proven equivalent by some like large tree of all of these inductive equivalence things. What I have to use somehow is the inductive principle on the on this induction here, which just sort of seems like pain. Linear algebra tensor product. All right, how can I get out this? Because I think I was sort of exploring this before. I was doing a bunch of simplifications, right? So you can simplify you can unfold a whole bunch of definitions, and at some point you get that you're doing a quotient, right? It's you're in some quotient type. Like the key point is that this type, this tensor product, is a quotient type. Can I try like quotient? Sorry. There's some way of like doing induction on quotients. quotient and it's probably something like this. It's probably like induction on or IND or something. Analog of quot dot induction on. Every element of quotient S is of the form of quotient make SA. Every element of quotient S is of the form quotient make SA. Right. So I guess the point is that this is of a quotient type as well. It's so annoying that it like has this sort of motive. I feel like this never actually appears. Motive quotient S to prop. Quot dot induction on. Quotient dot rec. See, it's very hard to like read this. I wonder what would happen if I simply tried to apply this, right? Q of type quotient S, right? So, right, so like if I unfold this and I simplify something, it's a free add monoid. Q hat is a free add monoid of list. It's definitely like a quotient. It's definitely, sorry, what point does it most seem like a quotient? This one is definitely of type quotient. Does this one describe itself as of type quotient? It does. What about this one? What about this one? What about this one? This one also describes itself as of type quotient. Okay, so what happens if I just say apply quotient dot induction on? Invalid field notation. Well, this is not the right induction on. Failed to elaborate eliminator. Expected type is not available. I mean, the thing that I'm inducting on is this. Every element of quotient S is of the form quotient.make SA. Like what I sort of want to do is apply this. It's not to C. Apply failed. Failed to unify motive with C equals 0. What I basically want is the left-hand side of this thing, right? What I want is this bad boy. Happens if I'd like tell it to do this. Failed to elaborate eliminator. Yeah. Okay. It just doesn't know what I'm trying to prove, basically. this is the sort of annoying thing to me, right? Like, what am I trying to think of? It's like I did all this simplification here. Simplify, 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 simplify. The point is that this is some quotient type. The point is that this is a quotient type. And the definition of equality in a quotient, like for quotient types, is that it's two things are equal if the underlying relation holds for them. So how do I get that? Is it like, let me like try this. So I feel like this one is sometimes better, like induction, setoid equal if setoid eq if rel eq. Yes. Wait. No, this is not what I was looking for. I'm a little confused by what I'm reading here. Setoid, sorry, what is setoid? What is a setoid? Choose setoid. Go to definition. Choose setoid. Go to definition. Or better yet, go to the definition of setoid. Setoid. A setoid is a type with a distinguished equivalence relation. Right? It's a type with an equivalence relation. It's just a type class. Yes. So what I really want is sort of like quotient eq. If there's really nothing like this, quotient eq. What I want is a theorem that a quotient dot make. Yeah. It's like this, basically. Quotient, I make A and I make B into the quotient type, right? These are the things that lift A into the quotient type. And this holds true if the setoid relation holds for A and B. So this is basically what I want. I think the issue with trying to apply that here, though, is that I have quotient.make on this side, but I don't have that zero. I don't yet have that zero is a quotient. Even though in theory that should be true, because as that other like induction principle said, everything should be like a quotient of something. Every element of a quotient type is the lifting of something. What happens if I rewrite this? Did not find instance of quotient make this equals quotient make that. So the thing that I want now is like if I mouse over this, so this is in if I go all the way back here, 0 is in Q hat. So like can I make a I have the it is the case that there is right. The problem is that it's like it's the type that the type that I think we lift from, right? Like when I do all these unfoldings, it comes out to some like list, free add monoid list. Like what I should be able to say is like It's a list of q times z hats. Okay. So let me just we have that is the case that there exists a L, which is a list of q times z hat such that quotient.make of this list is equal to 0. Sorry, flatness. Flatness, it says, yes. Type class instance problem is stuck. This is often due to meta variables. 0 of type q hat. Obtain whole HL from this. So what if I now rewrite HL backwards at H or HL? And now what if I rewrite using this technique? It seems like it's succeeding, right? I don't need to unfold all this. Sorry. Oh, apparently I do need to unfold. Wait, what's going on? Yeah, so I can do that, and then I can do all this, and I can unfold. And now the rewrite succeeds. So now we have this relation. What is the quotient.out function, I wonder? Choose an element of the equivalence class using the axiom of choice. Okay, cool. Right. I guess the point is that this is quotient.out, right? Quotient.make. I can do something like quotient.make of quotient.out. Yeah. Quotient.out eq prime. I can do this. Q 0. What I can do is something like this. I can do rewrite. Sorry, the name of the lemma is quotient.out eq. Out eq at h. The thing is, I'm doing it backwards, and I would like to actually supply that my argument is 0 of type q hat. Fail to emphasize. That's interesting. If I do all of this and I get to this point, can I do this now? Can I do this? Yeah, that one works. And I can do then that one. Setoid.r. Right, so this is the relation. And what happens if I call sip now? Sip made no progress. How can I unfold? this setoid. Right. So the point is that this is known to be the setoid in question is this setoid. Tensor product equiv. Can I just write unfold setoid dot r at h? Yeah, so now I have this add con gen statement. Right. I feel like somehow what I want to do. So I want to like prove that if I'm trying to prove that that's not equal to 0. Maybe it would be like good to like go and revisit like what does it mean to be like flat? Flatness is the like critical. Where was I? It was like here or something. This follows from torsion freeness, implying flatness for Z. Right, Z is torsion free. This is done apparently. What does it even mean to be torsion free? Let me like look at that. Does it does the dependency, right, the injective, it apparently needs the torsion freeness. It's probably in here as well. So if I search for tor, then is the positive natural, and the function which takes an element of z hat and multiplies it by that natural is injective. I like see how this is proved. Function injective. Right, this intros, right? So what we intro ultimately is that, yeah, this equals 0, then it's 0. Seems like relatively easier for this because this type is not a like a tensor product. It doesn't have this big all this like rigmarole with like the quotient types. Right, this is what I'm trying to prove, I think. Yeah. flatness. Flatness for Z. What is flatness? What does flatness even mean? There's no definition here. Flatness for ring. Flat morphisms. Flatness is a local property. Oh no, it's using terms that I don't know. The module over a ring is said to be flat if the functor is exact. I don't know what that means. Faithfully flat. Morphism rings is said to be flat if the functor is exact. Free and projective modules are flat. Flatness is a local property. Okay. The functor is exact. This is like, it's not like, it's a term from category theory, which again is a field of math where they just make up words for simple concepts. Sorry, exact functor. Exact functor. Whatever between categories is exact if it prefers the exactions of sequences. Right, I remember this diagram from my abstract algebra class, but I don't remember what it means. It's an exact sequence. Yeah. Okay. I'm not sure if I'm going to get anything out of that. I feel like I still understand intuitively why this should be true, though. Like, if I go back to what I'm trying to prove, right, I feel as if I understand, right, I do this, right, so that I can unfold the setoid thing. I have add con gen here, and I have the tensor product equivalence here to setoid. What happens if I like simp now? This doesn't do anything, right? No. Tensor product dot equiv. So wait a minute. Add con gen, right? So like both of these are relations. Add con gen is like a completion of this relation, right? The equivalence relation is this relation, which is defined inductively. Sorry, just go to definition again. The equivalence relation is this inductively defined relation. The add con gen extends that relation with some more closure operations, also sort of defined inductively. So in some sense, we just have like a big sort of closure. Add con gen. Free add monoid of list. Like, so what I basically want to do, quotient.out1. Sorry, quotient.out prime of 0. So this is what I get out from 0. The question is, how is 0 defined, right? In some sense, that's the real question, actually. Maybe I should not have been doing that. Maybe this step is actually wrong. Maybe what I should have been doing is trying to like unfold what is the definition of 0. Like unfold q hat dot 0 at h. Sorry, I need to capitalize things. Maybe it's this. Sorry, so what is it representing to me? So it has this of net q hat 0. So q hat is obviously, okay, q hat is defined as this tensor product of modules, which must somehow, like, there must be some instance of 0 for this tensor product here. The question is, where is it, and like, how do you refer to it? Q hat 0. Like 0 val. Tensor product add 0 class. How is it defined? Like a tensor product over some module R. Add monoid. So it has add monoid as well. Add 0 class, add. Where is its monoid instance? Do the tensor product basic. Tensor product is defined here. Add is defined here. Add 0 class. It should just be the empty list, right? That should be, I mean, what I should be proving, where am I? What I should be proving here, right? So I can reduce this to its like list form. But the point is that 0 should be an empty list. I wonder if I can find it this way. If I have this, if I put in an empty list, and I say that this is true, 0 of type q hat by simp. Sorry, if I enclose this and solves goals, all. Yes. Okay. So this seems right. Now this is a much better thing to have. In fact, in some sense, right? It's a list, pre-add monoid of list. It's equal to 0. So what I want to be rewriting with this. Cool. So I rewrite with this. This one I can clear this. So I have this. Then I apply the quotient equality, right? So setoid R, we're getting closer. Setoid R for these two things. Unfold setoid R. I wonder what happens if I simp here. Feels like one way. It feels like this could be simplified, but yeah, sorry, simp at h. Yeah, okay, so this does simplify. Or no, it just sorry, does it just like simplify the like we add mono 0. Okay, what happens if I just start unfolding So I have add_congen, and I get this add_congen rel. Add_congen rel, this is the thing that is like explicitly defined. Yeah, has a nice definition, nice inductive definition. And tensor product equiv, pre-add monoid of. Sorry, what happened? Can I go to the definition here as well? Yeah, inductive equiv, this one as well. So I've reduced everything to like the two inductive definitions. Reduced everything to these two inductive definitions, and now I just need to proceed. And the point is that I should not be able to establish should not in fact be able to establish this at all. I should not be able to establish this relation if C is not equal to 0. Sort of thinking contrapositively here. How do you, right, so it's an inductively defined relation. How do you prove that an inductively defined relation is not true? You have to use the induction principle somehow. Maybe I literally do just need to like take the constant positive, like positive H. Is it by contra? What is the syntax? Why is it not giving me any information on the mouse over? Reduces the goal to proving false using the additional. Oh, it's contrapose. Sorry. What just happened? It's contrapose. Exclam. Right. Bilinear map. Right, it comes with a canonical bilinear map. Right, that makes sense. How do you prove a statement is not true of the natural numbers, right? Like for any natural number. You first have to you have to prove by induction that it's not true. Induction C using unexpected token. Unknown constant. What? Free add monoid induction on. I'm confused. I don't really. This is not right. It can't induction. It shouldn't be we shouldn't be mentioning C. Induction E, where E is an expression, generalizes E. Generalizes E in the goal. And performs induction on the resulting variable. Is there a free add monoid induction? I mean, what I want is this induction principle. Tensor product dot equiv induction, right? I don't think this is right either. When you induct on some natural number, right, it has to exist. Maybe I didn't want to contrapose. Maybe I'm dumb. Okay. Maybe I should be doing the outer one. I want to induct on H using adcon general. Maybe no. Sorry. Is it possible to just not induction E, induction H? Okay. Is this possible? Consider using the cases tactic instead. What happens if can I do the cases tactic? Cases H. Pendant elimination failed. Failed to solve equation C equals this. Let me read the induction documentation one more time. Induction. H with the problem is that it needs to be the right. I have okay. What do I have? Let me just try and think. What I have is this, right? I have that the relation holds. I have in my hypotheses that the relation holds. What this should allow me to do is prove that, like, if I can prove that the relation holding, right, if any of the like constructors, right, if I can prove for any of like the cases for how that thing holds, imply my goal, I should be okay. Induction H, what are the with? How do you get it to freaking autocomplete? The index in targets type is not a variable. Right. The issue is that these are not variables. It's not that I have some property of right. Like if I had a list, right? So like thinking of this as like the the like transitive closure. If I had a list, so I have one thing on one side, one thing on the other side. If I had a list of intermediate things, each of which was equivalent, I would then want to be able to like prove from the fact that those were equivalent. And I would want to be able to do induction on the list. So I would have some list L, right? So I would have that, I would have some list L. I would have the fact about the list that everything within it was a valid like instance of the relation. I would have the fact about it that every pair of adjacent things in it was a valid instance of the relation, and then I would want to be, and then it would be that should be equivalent to okay, let me just like try and conceptualize whether or not that like is it the case that this like stupid statement is true for like any ring or any like sufficiently like any like normal ring? Is it true for Z, for example? I wonder if I can like prove that separately. It's like what happens if I like what happens if I do that? Like what happens if I like take all this like okay, forget about this abbreviation. Include left is the name of the abbreviation. What would happen if I wanted to like prove sorry, what is the include left of type Q sorry, I'm just gonna try and replicate this Q of this type, right? But instead of Q hat, which is sorry, if I go to the definition, Q hat is this. What? Why is it? Why is this not right? I've just replaced it by its definition. Expected token. You had. Did I like leave the abbreviation zone? Ugh, oh my god. I'm just gonna forget about this. Abbreviation foobar q what's our z? Okay, even this is wrong. What is the issue? Where does this go? Q hat is here. Can I put this here? Expected token. What is the issue? I'm totally mystified. This is insane to me. You're telling me this is valid syntax, but this is invalid syntax? What happens if I change the order? Then it complains about this? Huh. Okay, well this is just confusing. Expected token. It only complains about the second one. Man. It's also annoying that the abbreviation. I mean, like one thing that's annoying is that like this is not like fully spelled out as abbreviation because every other keyword is like a full word rather than a part of word. But it's also, I don't understand how it's possible that this could be complaining like this. It should just be exactly the same. What happens if I do like this? I mean, okay, so if I go, sorry, if I remove the notation, tensor product RMN is the name. So it's tensor product Z, I believe it's tensor product, let me get the order right, MRN, right? So it's tensor product ZMN. So Q hat is tensor product ZQ Z hat. Whereas what I am trying to do here is, so this could be tensor product ZQ Z hat. Don't need to unfold this, right? This is the same thing that we had before. Right, this is the theorem I'm trying to prove. But what I'm interested in is the question of whether this is just true for Z, for example. Unsolved goals. Include left, apply. I can keep going and like this. And now 1 is a simple element of Z. C of type Q, and this. And like, that does like any ASOP work here? No, it's not enough. Apply quotient induction on C. Fail to elaborate. Z. What is Z? Well, it's just the integers, right? But what is the like key property of the like ring at hand? I'm just like trying to hook into, like if I can prove like a very simple version of this, at least I can hook into like how things of this form are proved. I can like find some part of the library to like start to learn what's going on and learn how to make proofs. Because obviously I'm not using the right, like, freaking induction thing. See, you would think that it would be like some form of just like a congruence closure. It's like a transitive closure of a relation, symmetric transitive closure of some relation. I mean, at some level, it's sort of weird that the API is not like that already, right? It's like all right, so this takes a relation and returns another relation. So it's like, see, it's very close to the definition of a transitive closure, right? If I were to just remove this, so M and M, right? They're the same type. If I were to remove add, do we have a definition somewhere in the library of like a transitive closure? Transitive closure. So this is the transitive closure. What I'm additive congruence relation, the inductively defined smallest additive congruence relation containing a given binary relation. I mean, like, first of all, this docstring is just wrong. It is not the smallest additive congruence relation containing a given, like, a congruence relation. Does that mean symmetrically transitively closed? Congruence relation. Relation based on how things are not full words here. Maybe this part of the library doesn't use full words. Transgen. Okay, transgen is the transitive closure. Refulgen is the reflexive closure. Is there a simgen? Reful transgen symmetric? Sorry, so we have refulgen, we have transgen, we have reful transgen. Sorry, I need to delete. Reful transgen. H is symmetric. Symmetric relation reful transgen. Reful transgen. Reful transitive. Okay, the reful transgen is the reflexive transitive closure of R. Yes, it basically tells you that we have R of A. This is a very weird way for this to look. Like, why is 1A provided before the colon and 1 after? I would favor both before the colon, and I could understand both being after the colon, but why is 1 before and 1 after? That's sort of strange. Relation reful transgen, right? The reflexive transitive closure of R. So, I mean, like, if, like, you can see why both of them would be after the colon, right? It's like I'm taking a a relation on alpha, and I'm returning a relation on alpha. So REPL is to tell us that, right? Yes. So A and A, right? So A for itself, right? So the relation REPL transgen of R, right? This is the function this is the like relation that we're computing, right? And the first thing is to tell us that for any A, that relation that we're computing holds for A with A. Yes. Furthermore, it holds for A with B. If it holds for A with B and for B with C, then it holds for A with C. REPL transgen. I wonder if does it have like a sim? Transgen is just the transitive. That's the other thing. Sorry. Is this right? This is so weird. Shouldn't there be like an of here? Like so I'm trying to like tell if this definition is even right, because okay, so we have an inductive, right? We have an inductive definition which, given a relation R, is supposed to give us a new relation R on the same base type alpha, right? The first thing we have is that the new relation that we're building holds for any A with A. The second thing that we have is that it also holds for any A, B. Maybe I don't understand what's going on here. Right, tail BC. But the question is, right, if I have, how do I establish, like, let's say that I have the type, okay, this is like, I realize I'm going like off on a tangent. The problem is that I don't see like the of relation here. I feel like there should be a third constructor which lets you say, okay, um, given that R holds for A and B, then REFL transgen of R should hold for A and B, right? It's a closure of R, right? And I'm not seeing that. Like for here, for example, if I look at REFL gen, there's this single relation which says that if I have R, then REFL gen RAB. It just doesn't look correct to me. And like the other thing that I want to know is like, where is the symmetric? Okay, so this is like this definitely seems wrong. Okay, I'm just gonna like, again, maybe someone can tell me if there's like a problem. Relation.REFL transgen. How do I even like, what do I even do here? I'm not like missing something, right? It's like, it's the case that like immediately afterwards we have Refulgen, which has this single thing, which lets us produce. It would just be so much nicer if there was more API related. Basically, like why am I going down this whole road? It would be very nice if instead of defined as this sort of like inductive type that I like, oh my God, I have to like use induction. Induction should not be present here, right? This file is too high level to be like every proof is like an induction proof. What would be much better is if there were some, okay, it would be nice to have something like this, right? So first of all, there needs to be something called relation dot uh, refl trans sim gen. I wonder if that's what it's called. Refl trans sim. Refl sim. Okay, it's just not. Okay, so like several things have several things. There should be something called relation dot refl sim trans gen, which gives me the reflexive symmetric transitive closure of a relation, which produces an equivalence relation, essentially, right? Equivalence relation. Like the other point that I sort of feel should be the case is that Refulgen, right, the reflexive closure and the transitive closure, right? It's this weird thing. It's like, can't you prove there's like this fun sort of like trick you can play on undergraduates where you say like, why is the reflexive property for the equivalence relations necessary to state at all? Why can't we say, oh, we can prove this because if we have the transitive relation, then we can say A uh, A goes to B and B goes to A. Therefore, from the symmetric, if I have A goes to B, then the symmetric gives me B goes to A, and then I have A goes to B goes to A. And from the transitive, I then have A goes to A. But the reason that that doesn't hold is that you might not have any outgoing arrows from A. So there's all sorts of like, yeah, this sort of needs to be triaged a little bit. Definitely does seems like this is just an objectively okay. Definitely seems like this one is just an objectively wrong definition. Because I'm pretty sure that this is just not right. Refulgen AB. How do they prove this theorem, though? Sorry, what's going on? Reful transgen. This is the one that I'm claiming doesn't have the fact that I want. The single. where was I? I felt like I saw a theorem that stated something that I thought was not provable under this definition. Refulgen to refultransgen. Okay, let me just like get my head on straight. Relation refulgen to refultransgen. If R AB holds, then R of AB holds refultransgen. It's furthermore annoying that they don't put this definition below the less complicated ones below, right? Refultransgen, reful tail. I don't see how you can prove, like, if the underlying R has A equals B, relates R to B, if the underlying R relates A to B, then I don't see how you could prove that for refultransgen of R. Refulgen, on the other hand, I do see how you could prove it, because you could use single. Therefore, I don't understand how this theorem can be true. Source. MATLAB logic relation. Sorry, MATLAB logic. I can be doing this in the interactive. Line 278. To refultransgen. Right. So I need to be able to prove refultransgen. No. Okay, this makes total sense, in fact. No. Yeah, sorry. I understand. So this is provable because this is this relation is weaker than it's supposed to be. And so like if it were stronger, it would be even stronger. Okay. I think I'm just confident this is just bugged, right? Okay. Okay, this has been fun working on this, but we've found an excellent opportunity to give up on that and do something that will be perhaps a little bit more valuable and also successful, which is to try and fix this over here. So if I go here to master, sorry, what's the name of the file? MATLAB logic relation. Let's close this. MATLAB logic relation. It would just be like much better in general if more of this file were proven like in a way where, refultransgen was constructed as refulgen of transgen. This is like a fun fun prank to pull on the MATLAB people, because so let me just think this through. It should be the case that refultransgen, like the way it should be defined, this is the reflexive transitive closure. It should be the case that the reflexive transitive closure is equal to the transitive closure of the reflexive closure of that relation, right? Because if I take the relation, I take the reflexive closure, right? The resulting thing will have all the things in it. Yeah, I think those two things are equal. such as equivgen. Where is eqvgen defined? EQ. It also doesn't help that like none of the like the so sometimes this seems to be called single, sometimes it's called of, sometimes it's called rel. That seems to be inconsistent. Okay, I need to be like noting these things down. Let me like open. If I go to the file where I incessantly complain, it's this file. So here's where I complain. The complaint that I want to make is that equivgen no, but sorry, this is in I don't know why I'm in the Imperial College London docs. I don't want to be there. I want to be in the normal docs. Please take me to the normal docs, please. EQVgen. Where are the normal docs? Athlab docs. This one. EQVgen. So this is the link. So EQVgen uses, okay, the relation library needs to be cleaned up. Closure operations refer to things differently. Uses, so this one uses rel, yes, rel for the constructor, the base relation constructor. Transgen, relation transgen, uses, does not have it at all. Okay. Copy link. Have it at all. Refulgen uses single. No. No, yes, single. Single is what they're using here. All right, so here they use single, and the analogous thing for equivgen is rel. Full tail. Sorry, Breffel transgen does not have it. No, sorry. Refulgen has it. Sorry, Refulgen is good. Refulgen has it. Transgen calls it single. Two. Does not have it at all. This one doesn't have it. This link should not work, of course. Yeah, it doesn't exist. It's fine. So single, this one, okay, this one doesn't exist. Sorry. Okay, this is another point. This one is like this one is a broken link. That function does not exist. That def does not exist. Doesn't even exist. Single does not have a base relation constructor at all. The definition is bugged. And there was another, where else was I looking at it? It was like the add congen, right? Add congen source. Add congen rel calls it of. Congen.rel, sorry, what is it? Congen.rel. I guess this is like this is the, yeah, to add, so this one. Congen. Sorry, let me just copy the right link. This one uses backtick of for the base relation constructor. Okay, so several things here. I think the main thing that I want to do is fix the bugged one, because that seems like a pressing issue, potentially. The one that I'm claiming is bugged is Ruffle Transgen. Reflexive transitive closure. There should also be like a symmetric closure, I feel. Sorry, is that like equiv gen? EQV gen? The equivalence relation, yeah. So this one is the equivalence relation. This one is defined in MATLAB and init. Because I suppose it's necessary to have it that high up because we have the quotient and such. Still, one feels like it would be nice to have all 8. Or even if you don't want all 8, just like as many of them as you wish. The further thing is that it's like Ruffle Transgen. Did I not? Where am I? Ruffle Transgen. MATLAB logic relation. This one. Cases tail if. I feel there should be another case called single. I mean, like, mainly I feel that the single case should like be have like primacy maybe. And even more than either of those things, I feel what should be done Raffle transgen. I feel what should be done is this. So we have RevelGen, and I feel like this should be moved down here. And I feel that this should in fact be totally changed. Alpha to alpha. Sorry, I'm like I need to like have this be building. Please fetch the MathLab build cache. Okay, so the Raffle transgen is going to be a much more simply defined thing. Transgen RaffleGen R. Of course, it did not need to put all that stuff down because I defined you just here. I'm defining this like this. I don't know if these alignment statements, I guess the alignment statements, I don't know what those are like for, yeah, I don't know, MathLab 3 or whatever. And I think that this attribute should be gone because now the Ruffle transgen Ruffle is just the transgen Ruffle, I believe. It should not be inductive furthermore, it should be a def, I think. Only applies. Yeah. Right. So I've done this, and now I've broken everything. But the key important thing is that I made the change that I was supposed to. Now Raffle transgen is now just the transitive closure of the reflective closure of R, which I think is fine. So Raffle gen implies Raffle transgen. So this is a theorem. Let's now prove the theorem. Oh my god, why is it not doing this? Away by... sorry, I need to get out the info view. So Ruffle transgen, the outer one is the transgen, and what I want to be applying is the single. Apply single. Fail to unify Ruffle gen with Ruffle transgen. Single. Yes, I want to be applying single. Transgen.single. In fact, I don't necessarily see why it has to be like the convention in MathLab is to put the colon later, right? So it should just be the case that like A and B are of type alpha. And I can furthermore, if I want to, put an H here so I don't have to do this. I can put my colon here. I don't have to do this. And this is in fact an exact statement. And because of an exactness, I can just delete this, and therefore I have this. Okay, cool. Seems like a theorem to me. What else is broken? Right, trans. HAB, HBC, ruffle transgen, bye. Aesop, unknown tactic, cool. Yeah, ASON is like, that's like some JavaScript thing. The main thing I want to do is apply, right? So yeah, so it's going to be an exercise in just applying the things, right? So now I want to apply, so I have ruffle transgen, I apply transgen.single. Now I want to apply transgen.trans. Transgern.trans. Invalid field notation. Sorry. No, it's called tail for some reason. That's another question. Why is transgen, why is the transitive constructor for transgen called tail and not, I don't really get that. It should be called trans, right? It's called tail though, apparently. I apply this. Tail. HAB. HPC. What's going on? I apply transgen. What I want to prove is ruffle transgen.trans, yes. Why do I get out rufflegen RBC? Okay. Yeah, nightmare of like thinking clearly. Let's see. Transgen.tail. Oh, okay. Maybe this is related to it. Well, no. I mean, so it's yes. I see what it does. Transgen.tail. I see what it's called tail. Okay, no. That actually makes perfect sense. I'm the dumb one. The reason it's called tail is because I was misreading it. This is not transgen RABC, RBC, transgen RA. Right. I had not read this line. I had thought this line of code read transgen RABC, transgen RPC, transgen RAC. But that's not what it reads. But yet again, like why? I guess the point is that this was defined before these other two. And that's why this is wrong. So transgen, the point is that there is somewhere in this file something called transgen.trans. There's probably like a section. If I delete, yeah, transgen trans, here it is. So the key, yeah, so what actually has to be done? What actually has to be done is that this has to be deleted and moved to the bottom of the file. So here we have the transgen namespace. Refulgen, transgen. We have a bunch of theorems about refulgen and transgen. And now we have yet another section on reful transgen here, which I will now paste. Yeah, so experiencing errors. Save. Is there an error here somewhere that I'm not seeing? Sorry, here. To reful transgen. Yeah, so if I have transgen, so previously I proved reful transgen, sorry. Previously I proved that refulgen implies reful transgen. Now I am proving transgen applies reful transgen. Cool. I think that the way that I do this, right, so like just always so that I can see things clearly, right? Transgen. Cases. I think what I want to do is cases. Or by cases, I think is the. I mean, like more than anything, I just want to like keep the same process that I already have, right? So all of this looks fine. The point is that from RAB, I want to be able to prove this. And the point is that I now simply have to apply the right constructors, two of the right constructors. I need to apply single and then single again. Apply single, dot single. The first thing I have to apply is the reful, the transgen dot single. Exact. Here, I apply something like this. Wait, what? Try this. Cool. And of course that can be golfed. But whatever. Trans left. And now transgen, reful transgen, transgen. Yeah. Okay. Well, I've been at this. Let's see. This is gonna like take a while to correct everything for the rest of this file, but it seems like I'm on the right track. I think what I'm going to do for now is just save this and come back to it. Let me like finish making the pull request. So I'm in master. I would like to now create a new branch. Fix. Reful transgen. I'll go to this file so that the file is open. I will commit. Sorry, I don't this, commit this, she'll commit, watch that branch, now return here, and I can go to like MATLAB or on the top level, compare and pull request. It's like, I don't know what are the, let me like recall what are, like if I go to the lean prover community, and I go to like the naming conventions, or the commit conventions. Feat fix. So this is really a fix, I guess. Fix. Ruffle. And seems like this current definition of the reflexive transitive closure does not insist that missing constructor for the base relation and dealing with this. Well, yeah, I mean, the main thing is that this is missing this. But that seems like a, yeah, so I just need to like go through. It would just be nice to like go through. See, what would be like the most nice of all would be to like define the reflexive closure, define the symmetric closure, define the transitive closure, and then define the like equivalence closure, the like reflexive transitive closure and the symmetric reflexive transitive closure as compositions of these concepts. The only problem with that is that at the end of the line we have the equivalence thing, which is actually in MATLAB, which is not in MATLAB. It's in like base lean, which makes it hard to like change that. But that definitely seems like a better way of doing things, because I would rather not have to like prove equivalence relations. Like it would be nice if, like, for example, the relation for the like adcom monoid or whatever could be defined like as a closure, right? Like by applying a closure operation to some other relation. But perhaps that can be done. Yeah, so that seems like a good, like, seems like we have another nice PR to. I don't know exactly why Kevin is the like request, like suggested reviewer here. That seems like progress has been made. Okay, that seems like good enough for today.